Last lesson today in our solution chapter. Last time and the time before, we worked on colligative properties such as boiling point elevation and freezing point depression. And today we're going to use either the boiling point of a solution or the freezing point of a solution to determine the molar mass or the molecular mass of a solute. So we're focusing on the latter piece of the learning goal, and ultimately we're going to want to determine the molar or molecular mass of a solute, and it's determined from the freezing point or boiling point of the solution. And we had a whole series of formulas the other day, and we're basically going to push them through backward. So what we're looking at here is that we were able to calculate the freezing point of a solution in two steps. In the first step, we calculated delta TF, which is equal to the KF times the molality times the I. And in the second step, we were able to calculate the freezing point of the solution by subtracting the delta TF from the freezing point of the solvent. Remember that the solution's freezing point is depressed, so it's going to be less than the solvent, so you subtract. Well, we're going to use these formulas today in a backward fashion to determine the molar mass of a solute. And be careful with molar mass. It's a capital M. It looks like molarity. Our unit will be grams per mole here, though, and then you'll know it's not molarity, but rather molar mass. Now, similarly, we were able to look at boiling point as well, so we can calculate the delta TB by doing the KB times the M times the I, and the boiling point of the solution is equal to the boiling point of the solvent plus delta TB. And that's solvent here. Let me write that out in case it's not clear. So depending on the information provided, if you're giving the freezing point of a solution through a series of steps, we can get the molar or molecular mass of the solute. Alternatively, if you're giving the boiling point of the solution through a series of grossly similar steps, you can get the molar mass of the solute. So our goal today will be to determine the molar mass of the solute. This can be extremely helpful in crime scene investigations. If you find an unknown substance somewhere, you could do some types of analytics on it, and you could determine maybe the freezing point, the boiling point, and in turn, the molar mass of that particular substance. When we calculate or determine the molar or molecular mass of substances, there are four main steps that we're going to follow. Now, I've written all the steps out for you, but I really want to show you the derivation, because while I will give you some basic formulas such as this or this, I won't tell you if you're adding or subtracting. I'll put plus or minus, because you should know the boiling point gets elevated and the freezing point gets depressed. So if it gets depressed, you subtract. If it gets elevated, you add. But from these formulas, you will be able to follow through on the four-step process to determine molar mass of the solute. It may not click together right away, but as we walk through a few problems, I think you'll feel very successful with this type of analysis. So those steps are listed there. I want to walk you through. In these problems, you will be provided with typically, let's say, the boiling point of the solution or the freezing point of the solution. You will be given the mass of the solute in grams, and you will be given the mass of the solvent probably in grams as well. You also will be told what the solvent is. And from that information, you can determine the molar mass of the solute in grams per mole. The way we're going to do this is we're going to work the formulas you were provided with the last 2 days backward. So in the first step, which we'll call A, that's how I labeled it in your notes, you want to be able to calculate delta TF or delta TB. However, the way we calculated it previously will not be an option because you don't know what the solute is, so you can't get its molality initially to get its delta TF. So you're actually going to work the second formula backward to get the change in, because you'll be given the boiling or freezing point of the solution, and this you can look up provided that you know the solvent. So if I wanted to calculate the delta TF, I know that the freezing point of the solution is equal to the freezing point of the solvent minus delta TF. I want to get delta TF by itself, and I really don't want it to be negative. So if I add it to both sides, I have that. And then I want to move this to the other side, so I'll subtract this from both sides. And I'll have delta TF is equal to the TF of the solvent minus the TF of the solution. Now, if you have trouble manipulating that formula, you can cheat it a little bit. The delta has to be positive. So you always will subtract the smaller quantity from the larger quantity. Keep in mind the freezing point of the solution has been depressed, lowered, so it has to be smaller than the freezing point of the solvent. I'll work TB in a sec. I don't want to flip back and forth because I think it will be confusing to you. So to calculate the change in freezing point, you'll subtract the two freezing points, the larger quantity minus the smaller one. In step B, you want to calculate the molality. Well, that you can get by working this formula, the first one we used the other day. In these problems, you're going to have non-electrolytes, and their I's will be 1, so you don't need to deal with I. And you can calculate molality by dividing both sides by KF. And so you have molality is equal to delta TF over KF. So that's the second thing you're going to do. Say it again. I is 1 because you're going to have a non-electrolyte as your solute. It's not going to be ionic. I will be 1 for covalent compounds. It just makes it easier. In step C, you want to calculate moles of the solute. We know that molality is equal to moles of solute over the mass of the solvent in kilograms. So if I wanted to calculate the moles of solute, what would that be equal to? The moles of solute is equal to the molality times the mass of the solvent in kilograms. You multiply. This is the most common error that I see. And we're going to be using all these steps several times in our practice problems, and you should be very successful with it. And then finally, in the last step, you want to calculate the molar mass or molecular mass of the solute, and that's going to be equal to the mass of the solute, which is given, over the moles of solute that you worked so hard to get in the previous step. And what you can see here is you basically have a chain. So these steps must be processed in the correct sequence. You get delta TF, and then you use it to get the molality, and then you use the molality to get the moles of solute, and then you use the moles of solute to get the molar or molecular mass of the solute. The only difference with boiling point is that with boiling point, we're going to alter the first two steps ever so slightly. If you were working in terms of boiling point, delta TB would be the boiling point of the solution minus the boiling point of the solvent, because the solution's boiling point is elevated. Again, the larger quantity minus the smaller one. And to calculate molality, you would have the molality is equal to delta TB over KB. So those would be the two changes. We're going to do freezing point. We're going to do molar mass determinations based on freezing point first, and then we'll switch over to boiling point. But again, the change is very subtle. I don't think you'll have an issue with it. All right, let's walk through a couple of examples. Keep the steps right in front of you because you're far more likely to be successful. And again, with colligative properties and these molar mass determinations, it is a little more challenging. There are far more steps than what you were quizzed on earlier in the week. In question 1, it says, when 27.3 grams of a non-volatile molecular substance, that means I is 1, is dissolved in 300 grams of water, the solution begins to freeze at negative 0.49 degrees Celsius. What is the molar or molecular mass of the solute? So in question 1, the mass of the solute is given, and that's something you don't use until the very last step. The mass of the solvent is 300 grams of water. You need to know what the solvent is. and the solution begins to freeze. So the freezing point of the solution is negative 0.49 degrees Celsius. And from all of this, we want to get the molecular mass in grams per mole of the substance. Other information that's not given directly but will be very helpful. Your solvent is water. I'm given a freezing point of solution. So that means I'm going to need the freezing point of the solvent, which is water. Water, of course, freezes at 0 degrees Celsius. I'm also going to need the Kf for water, and that information, as you have seen previously, can be obtained from the back of the periodic table, focusing on the last two columns, the freezing point of water, and the Kf for water is 1.853 degrees Celsius kilograms per mole. And now we're ready to rock. We're just going to go step by step, very slowly. I'm going to label the steps. You don't have to. It may be helpful to you. In A, I first want to calculate delta TF. And again, this is the freezing point of the solvent minus the freezing point of the solution. You've got to get a positive delta TF. If you're not sure what to subtract, try the combinations. And there's your delta TF. It's positive. In the second step, you want to calculate the molality, and you do so by dividing the delta TF by the Kf. You have 0.49 degrees Celsius over the Kf, and that's why sometimes it is helpful writing the information down. I really want you to watch the units here. Degrees Celsius cancel. I have 1 over kilograms per mole. What is 1 divided by 1/2? 2. So 1 over kilograms per mole is just moles over kilograms. You just flip it. And that's a unit for molality. Kids often have the wrong unit there, and it can cause problems later on. And that's 0.26 moles per kilogram, or molal. In step C, you want to get moles of the solute, and that's equal to the molality times the mass of the solvent in kilograms. I've got the molality right here. The mass of the solvent in kilograms, move the decimal 3 to the left. And that's equal to 0.078. Note the cancellation of kilograms, and that's your moles of solute. The most common mistake I see is here. Make sure you multiply these quantities. The kids try and divide them, and if you watch the units, you won't do that. Make sure you have units everywhere. And then in step D, molar mass is equal to the mass of the solute in grams over the moles of the solute that you worked so hard to find. The mass of the solute was given initially 27.3 grams. We're going to divide that by 0.078 moles. And we have 350 grams per mole. So it's a 4-step process, which is shown here. And if you use these 4 steps and you really keep track of your units, you should be extremely successful with calculating molar or molecular masses of substances. Not so bad, is it? It's a lot of steps. And with practice, you'll be very good at it. Let's do another one. You'll walk me through more than I walk you through on this one. Ready, ready? The next problem says, when 10.6 grams of a non-volatile molecular substance, that's the mass of what? Solute, is dissolved in 325 grams of cyclohexane, that's the mass of my solvent. What's the solvent? Cyclohexane. The solution begins to freeze at negative 3.24 degrees Celsius. We want to know the molar or molecular mass. Let's get it down and let's see if you can get it to rip. It looks like some of you are way ahead of me already because you like to figure it out yourself, which is good. The mass of the solute is 10.6 grams. The mass of the solvent is 325 grams of cyclohexane. The freezing point of the solution is negative 3.24 degrees Celsius, and we want to know the molar mass in grams per mole. What other information, what might we pull out? What else will be helpful to know in regard to cyclohexane? Freezing point, and that is 6.54 degrees Celsius, and what else? The KF, and that is 20 degrees Celsius, kilograms per mole. What's step A? We're going to get the change in freezing point. And what will we subtract from what to get a positive delta TF? You got it. 6.54 degrees Celsius minus negative 3.24 degrees Celsius. And that's 9.78 degrees Celsius. In B, we want to get the molality. What do I divide? Delta TF by KF? Now I've got the molality. What's the next step? We're going to get moles of solute, and what do we multiply? The molality by the mass of the solvent in kilograms. So we've got 0.489 moles per kilogram times 0.325 kilograms. And in the last step, how do we get the molar mass? It's got to be grams over moles, right? Grams was given. We worked very hard to get moles of solute. And that's 66.7 grams per mole. Four-step process. The more practice you get, the more successful you will be. Questions? I think with our problem-solving day next time, we will hold on 3 and 4 for those of you who may not be here. On 3, the problem is grossly similar, except they tell you the temperature at which the solution boils. So you'll work the first 2 steps ever so slightly differently. And the only other way they can try and trick you is actually by making it easier, but you might not recognize it as such. In number 4, it says the boiling point is raised by 25 degrees Celsius. So they're not giving you the boiling point of the solution. Instead of giving you the boiling point of the solution, what are they giving you in number 4? The change in boiling point. So they give you delta TB. You're basically skipping the first step. But we can work 3 and 4 together next time, and I can record that just so everybody has it. At this point, hopefully, at least with freezing point data, you feel comfortable determining molar mass of a solute. Questions here? And we will go over the boiling point aspect next time so that we don't rush it. Questions?